Welcome to The Explainer. Today we're doing a deep dive into one of the most persistent and frankly costly challenges in gas processing, foaming inside amine treating units. For any of you who've worked in a plant, you know this is the kind of problem that can give you nightmares. So we're going to break down the core science, get into the root causes, and look at the engineering solutions for an issue that can bring a multi-million-dollar operation to a grinding halt. Let's get right into it.
All right, here's our roadmap. We'll kick things off by framing the problem and its real-world impact. Then, we'll get into the fundamental physics of what makes a foam a foam. After that, it's all about diagnosis. We'll look at the usual suspects, the contaminants, and then the inside jobs, degradation, and operational issues. From there, we'll shift to solutions with the engineer's toolkit for mitigation and wrap up with the emergency playbook for when things really go sideways.
So let's start here. What are we actually talking about when we say amine foaming? Because this is so much more than just a few bubbles on the surface. It's an issue that fundamentally undermines the entire gas sweetening process.
At its most basic level, foaming is a mass transfer killer. You see, the whole point of an amine unit is to get intimate contact between the sour gas and the liquid amine. But when a stable foam develops, it creates this thick, bubbly barrier that physically blocks that contact. The amine simply can't do its job, which is, of course, to strip out those acid gases and clean up the product.
And the fallout from that failure? Well, it's a domino effect, and it's all bad. You're not just looking at reduced efficiency, you're looking at off-spec product, which is a huge financial hit. Operationally, you risk flooding the entire tower, which can then carry corrosive amine solution into downstream units where it absolutely doesn't belong. This damages equipment, you lose expensive amine, and worst of all, you're facing unplanned, costly downtime.
Okay, so to really tackle this, we have to stop thinking like plant operators for a minute and start thinking like physicists. We need to zoom all the way in and understand the life and death of a single bubble inside that absorber.
You know, when it comes right down to it, foam is just the result of a constant tug of war. Every bubble of gas wants to rise. That's just simple buoyancy. But the liquid amine solution is fighting back, trying to pull that bubble apart with surface forces or hold it down with hydrostatic pressure. The foam you see is just the outcome of that battle.
So the force pushing upwards, buoyancy, is pretty straightforward. It's all about the density difference between the gas and the liquid, the size of the bubble, and of course, gravity. When you have a massive flow of gas creating millions of tiny bubbles, this collective upward force becomes absolutely enormous. It's the engine that powers the whole foaming process. Now, the main force fighting back is surface tension. Think of it like the liquid's skin. It's that cohesive force between the molecules that makes the liquid want to minimize its surface area. To create a bubble, you have to stretch that skin, and the higher the surface tension, the more the liquid resists being stretched. So in a perfectly pure amine, it's actually kind of hard to make foam.
But here's where it gets really interesting. Surface elasticity. This is the secret sauce for a stable, problematic foam. It's basically the foam's ability to heal itself. As gravity starts to drain liquid down the wall of a bubble, making it thinner and weaker, any contaminants present create a surface tension gradient. This gradient actually pulls liquid back up into the thin spot, reinforcing it. It's this self-repair mechanism that turns a fleeting bubble into a stubborn foam.
And that brings us to this critical distinction. You have to think about tendency and stability as two different things. Tendency is just how easily the foam gets going. Stability is how long it sticks around. You could have a solution that foams up easily but collapses just as fast. That's not a huge problem. The operational nightmare, the thing that causes tower floods, is when you get high tendency and high stability. That's the perfect storm.
All right, now that we've got the physics down, we can start playing detective. Let's do some process forensics. What are the foreign invaders that get into our nice, clean amine system and start causing all this trouble? The real challenge for any plant chemist or engineer is that the list of things that can promote foam is frustratingly long. So let's zero in on the primary culprits, the ones that you absolutely have to watch out for and get out of your system. So at the top of the list, we have liquid hydrocarbons or condensate dropping out of the gas stream. Then you've got solid gunk, mostly corrosion products like iron sulfide. And here's an ironic one. Chemicals we add on purpose, like some types of corrosion inhibitors, can act as surfactants and promote foam. And just look at that last point. It doesn't take much. We're talking parts per million of things like fatty acids to start seeing a real problem.
Now, those solid particles are especially tricky, and it all comes down to their wettability. If a particle is hydrophilic, it's happy to stay submerged in the liquid.
If it's hydrophobic, it wants to get away from the water. But the real foam stabilizers are the particles that are somewhere in between. They migrate right to that gas-liquid interface, the bubble wall, and they just sit there, creating a kind of physical, armored shield that literally stops bubbles from merging and collapsing.
And that brings us to public enemy number 1, iron sulfide, FeS. This stuff forms when H2S reacts with the carbon steel in your pipes, and it just happens to have that perfect intermediate wettability to be a fantastic foam stabilizer. So here's the big takeaway. Controlling corrosion isn't just about protecting your pipes. It is a direct and critical anti-foaming strategy.
Okay, so we've talked about external invaders, but sometimes the call is coming from inside the house. Foaming can absolutely be an inside job, caused by chemical changes in the amine itself and, frankly, by how we're running the plant.
Your amine solution isn't immortal. It breaks down over time. In the high temperatures of the regenerator, it undergoes thermal degradation. And if any oxygen sneaks into the system, you get oxidative degradation. Both of these pathways are irreversible, and they create this whole cocktail of chemical byproducts that can completely change the physical properties of your solution.
And this data is just fascinating. Look at the different impacts here. You have things like acetic acid, which mainly just increase the foam volume by messing with surface tension. But then you look at piperazine and bicene. They don't really increase the amount of foam at all. Instead, they have a devastating effect on foam stability by jacking up the solution's viscosity, which means the liquid drains out of the bubble walls much more slowly.
Let's just pause on that piperazine number for a second. Plus 467% to the foam breaking time. What does that mean in the real world? It means a foam that might have collapsed in 1 minute now takes almost 6 minutes to go away. That is exactly how you go from a little bit of foam to a tower full of it in a hurry. And this really highlights the tightrope that process engineers have to walk every single day. You're constantly trying to stay within a very narrow operating window. Take temperature. The rule of thumb is to keep your lean amine inlet 5 to 10 degrees Celsius above the gas dew point to stop hydrocarbons from condensing. But if you go too hot, you speed up degradation. It's the same delicate balance with pressure, flow rates, and concentration. So, we've gone through the diagnosis, we know about the contaminants, we know about degradation. Now let's talk solutions. What's in the engineer's toolkit? How do we stop foam from ever starting, and how do we kill it when it does?
The first thing to accept is that there is no magic bullet here. There's no single fix. An effective, robust foam control strategy is always going to be a multi-layer defense. It's a combination of good mechanical filtration, some chemical adsorption and treatment, and just disciplined, precise operational control.
Prevention really does start with filtration, and a well-designed unit has what we call a full filtration train. Your first line of defense is a filter coalescer on the inlet gas to knock out liquids and big solids before they even see the amine. Then, in the amine loop itself, you'll have cartridge filters for the finer particles. And the final critical step is an activated carbon bed. This isn't a filter. It uses adsorption to grab all those dissolved contaminants that a mechanical filter could never touch.
And here's the proof that it works. This chart shows a beautiful, clean relationship. The more time the amine spends in contact with that activated carbon, the less it wants to foam. It's a powerful tool, but it's purely preventative.
So when prevention isn't enough and you already have a foam problem, you turn to reactive measures. You inject an antifoam. These are highly specialized chemicals, usually silicone or polyglycol-based, that have an incredibly low surface tension. The idea is that they spread across the bubble film like wildfire, creating a massive weak spot that causes the bubble to rupture almost instantly.
But, and this is a huge but that every experienced operator knows, you can definitely have too much of a good thing. If you overdose antifoam, it can actually make your foaming problem worse over the long run. The antifoam itself can start to act like a contaminant. So injection has to be a controlled corrective action, not a constant crutch you lean on.
Okay, so what happens when prevention fails? The antifoam isn't enough, and you are facing a severe foaming event that's threatening to trip the whole unit. Well, there's a very clear step-by-step emergency playbook. In a crisis, you have to be systematic. The absolute first move, before anything else, is to cut the gas flow rate. You have to stop feeding the beast. Right after that, you hit it with a shock dose of antifoam to knock the foam down. Then, it's all about stabilizing the ship. Watch your amine levels to protect your pumps, double-check all your operating parameters, physically skim any visible hydrocarbons out, and make damn sure your filters aren't clogged or bypassed.
And in a worst-case scenario where foam actually carries over and creates a spill, this whole response is guided by a universal safety framework. You've probably seen it before. rescue, confine, report, secure, and then clean up. The principles are always the same. Protect people first, contain the problem, and then communicate clearly and quickly to the control room and your response teams.
So, to wrap this all up, it's clear that foaming is an incredibly complex problem. It sits right at the intersection of chemistry, fluid dynamics, and process control. And while we have a pretty good toolkit to deal with it, the goal should always be prevention. And that leads me to a final forward-looking question for all of you. Are we stuck in this reactive mode, or could we get to a point where real-time chemical analyzers paired with AI and machine learning could actually give us a truly predictive model for foam control? Something to think about. Thank you for joining this explainer.
Like and subscribe for more.